Hi, I'm Victoria Brooks, and I'm going to talk you through how to calculate the sensitivity and specificity of a diagnostic test. Now, this might be a new test. Here it is still in its box. And we can do this by using a 2x2 table. Now, for the 2x2 table method, you need a population of animals in which you already know their true disease status. So, let's create a population of animals. So here we have an island somewhere, and on it we have some animals. Now these could be any animals that are similar to the population in which you want to use your new test. So we've already used a perfect test on these animals in what we call a gold standard test. And a gold standard test has 100% sensitivity. So an animal that's positive will always test positive, and it has 100% specificity. So an animal that is negative will always test negative. So you might be wondering, well, why don't we use this test, this gold standard test anyway, carry on using that one? Well, often they are expensive or they might be complex, so the test results could take a long time to come back, or you might need to kill your animals because your gold standard test is actually a post-mortem. However, we've used our gold standard on this population, and we found that 4 of our animals, our purple animals, are disease positive, and the other 96, so there's 100 animals that we've tested on this island, the other 96 are disease negative. So let's set up a 2x2 table over here. So that's 2 columns and 2 rows. So our columns are the true status of our animals. So this column is all our disease positive animals, and this column is all our disease negative animals. And we know that there are 4 animals in total in the disease positive column, and there are 96 in total in the disease negative column. So let's try out our new test. So we'll try it out on the disease positive animals first. So our test results go in the rows. So test status. So these are animals, this first row, the top row is the animals that test positive, and this row is the animals that test negative. So out of our ones that we know are disease positive, we find that 3 of them actually test positive, 1 of them tests negative. So these 3 are true positives on our test, and this one is a false negative on our test. Now, sensitivity is the probability or the proportion of animals that test positive given that they are disease positive. So we can get the numbers already for this from our 2x2 table. We've got 3 animals here that were testing positive, true positives on our test, out of all the animals that we know are disease positive. So we can write that as 3 divided by 4, which equals 0.75 or 75%. So that's the sensitivity of our new test. Now let's have a look at the specificity. So back to our population of 100 purple animals, 96 of them don't have disease. Now our test, most of them tested negative, so 92 of them in fact, and 4 of them, the animals that didn't have disease, tested positive. So the 92 are true negatives on our test, and the 4 are false positives on our test. So in terms of our equation down here, we know that the specificity is the probability or the proportion of animals testing negative out of all of those that do not have the disease, so disease negative, which equals, let's have a look at the numbers, 92 of them testing as negative on the test out of the 96 that we know don't have the disease. So let's write that down here, 92 divided by 96. Let's use a calculator for that one. 92 divided by 96 equals 0.96 or 96%. So lastly, some people like to label the cells of their 2x2 table. So you can do this. You can call them A, B, C, and D. Make sure that you've got the true status, disease positive and disease negative set up in the columns, and the test status, true positive and test negative set up in the rows like that. We can then say that sensitivity is our number of animals that are testing positive out of A plus C, all of those animals that have disease. And we can say that our specificity is D, the animals that tested negative out of all of the animals, B plus D, that didn't have disease. So lastly, this is not a perfect test. So when we come to use it on our populations in which we want to use this test, we need to then consider what we call predictive values. And we're going to cover that in the next video.